In this video, we are going to learn and we are going to derive expression for excess pressure, and we are going to derive Laplace law for spherical membrane as well as Laplace law for spherical bubble. I am going to give you the full details. I am going to derive the expression. I am going to tell you our theoretical aspect about the formation of liquid drop and expression for excess pressure in case of both liquid drop and liquid bubble. Before proceeding further, let us understand what exactly the difference between liquid drop and liquid bubble. Liquid drop is filled with liquid. It is a spherical ball of liquid, whereas liquid bubble is filled with air. Inside of the liquid bubble there is a air or gas. Liquid drop can rest on a given surface, whereas liquid bubble can float in air. Once the liquid bubble is formed, it starts floating, it starts moving in the free air. Liquid drop can have different shapes. Liquid bubble can be spherical or nearly spherical shape. Liquid drop has single surface, that is outside surface, whereas the liquid bubble has two surfaces. One is inside surface, another is the outside surface. Whenever the liquid drop and liquid bubbles are formed, then we talk about the two types of pressure. One is the inside pressure of the liquid drop and outside pressure of the liquid drop or bubble. And we need to find the relationship of this pressure difference and surface tension and the radius of the liquid drop or liquid bubble. The difference of this pressure is nothing but called excess pressure. Difference of this pressure and surface tension, the relationship between them is given by Laplace law. We can derive Laplace law for both the liquid drop as well as for the liquid bubble. So in today's video, I am going to talk about Laplace law for spherical membrane, and I am going to derive Laplace law for spherical membrane, and I am going to give you the theoretical information as well as I am going to support this theoretical information with mathematical calculation. So let us start today's topic, that is nothing but Laplace law of spherical membrane. Suppose we have a drop, liquid drop. Initial radius is R1 and inside pressure of liquid drop is Pi, I for inside. So Pi stands for inside pressure. Due to this pressure, its radius is increasing. Let us call the final radius is R2. So radius increases from R1 to R2. R2 minus R1 is nothing but delta R, increase in the radius of the drop. And inside pressure is Pi and outside pressure is Po. One more important point, that is inside pressure is greater than outside pressure. Therefore, the drop is assumed to be increasing in size. Now we need to calculate the two areas, surface areas. The area before expanding, that is A1, and area after expanding, that is A2. So surface area of the drop spherical body is given by 4 pi r square, and final surface area of the liquid drop is nothing but 4 pi and r2 square, that is nothing but 4 pi r2 nothing but r plus delta r. Initial radius we have taken as a r. Initial radius of the bubble is r. So 4 pi r plus delta r whole square. I repeat once again. I have taken r1 equals to r and r2 equals to r plus delta r. Therefore, final surface area of the liquid drop equals to 4 pi r square. That is 4 pi r plus delta r whole square. Let us expand it by using the formula a plus b whole square. A plus b whole square nothing but a square plus twice ab plus b square. So we get a2. What is a2? 4 pi. Here a square nothing but r square plus 2ab twice r delta r plus delta r whole square. Opening the bracket, we get 4 pi r square plus 8 pi r delta r plus 4 pi delta r whole square. That is a2. Now change in the radius delta r, that is very small change in the radius. If you square the smaller value, you will get further smaller value. So delta r square becomes further small. So we are neglecting delta r whole square. That means we are going to neglect 4 pi delta r square. This value is neglected. So 4 pi delta r square value, this value is neglected here. So what we get here? A2 equals to 4 pi r square plus 8 pi r delta r. We get this one. So this is the A2 value. Now after that, we have got A1 and we got A2. Now dA is nothing but change in the surface area. So change in the surface area dA is calculated by using formula final surface area minus starting surface area, that is A2 minus A1. So A2 value is 4 pi r square plus 8 pi r delta r minus A1 value, that is 4 pi r square. Now opening the bracket, so 4 pi r square 8 pi r delta r minus 4 pi r square. This and this cut down. So we get dA, change in the surface area, that is equals to 8 pi r into delta r. Call it equation number 3. Here the bubble is expanding in radius. So to expand the radius of the bubble, the work is done. The work is done in blowing it. So this work done in blowing can be calculated by using two different formulae. The result will be the same, but work done can be calculated by using surface tension formula, or the work done can also be calculated by using excess force formula. So first we will find out dW equals to surface tension into increase in surface area, and we can also calculate the work done by increase excess force multiplied by change in the radius of this drop due to increased pressure, due to increased inside pressure. Now we will calculate the work done due to surface tension. Call it dW1. So we call it by dW1. That is a work done due to surface tension. That is given by T into dA. So dW1 surface tension is T, and dA we already have 8 pi r delta r. This is the work done. the work done is stored as an excess surface energy. The liquid surface has energy, so that excess energy is stored in the drop. This stored energy can be denoted by delta E1, that is the excess surface energy. So surface tension is T and 8 pi r delta r. This is the excess surface energy. Call it as a dE1, denoted by equation 4. Now here is the excess pressure, that is Pi minus P naught, that is equals to excess pressure. We know that pressure equals to force upon area. This is a pressure equals to force divided by area. This is a basic formula. So Pi minus P naught, that is excess pressure, equals to excess force divided by area. So Pi minus P naught equals to dF. dF is the excess force divided by area, that is A1. Therefore dF equals to Pi minus P naught multiplied by A1. A1 nothing but 4 pi r square. So dF is nothing but Pi minus P naught multiplied by A1. A1 nothing but 4 pi r square. Therefore we get dF equals to Pi minus P naught multiplied by 4 pi r square. Now excess work done, again we get the dW1. We get the same work, but we are using different formula. Therefore here we can call it as a dW2 second case. They are same as earlier, dW1 equals to dW2, but to distinguish between them I have taken the here suffix 2. So that is nothing but excess force multiplied by delta R. So excess force is nothing but dW2 equals to dF, that is Pi minus P naught multiplied by 4 pi r square multiplied by delta R. This is dW, and this is the work done in blowing the drop. So this work done is also stored in the form of energy, and this energy is denoted by dE2. So dE2 equals to Pi minus P naught 4 pi r square into delta R. So we have the two energies. One is the dE1, that is the excess surface energy, and we have the dE2, that is a work done stored in the excess surface energy. But both are same, both energies are same. We had utilized a different formula to calculate stored excess energy, but both the formulae are same. Therefore dE1 equals to dE2. dE1 nothing but T into 8 pi r delta R, and dE2 nothing but Pi minus P naught multiplied by 4 pi r square delta R. Both side this R get cancelled, delta R get cancelled, pi and pi get cancelled, 4 ones are 4 twos are. Therefore Pi minus P naught equals to twice T divided by R. Pi minus P naught equals to twice T upon R. This equation nothing but gives us excess pressure inside the drop, and it is expressed in terms of surface tension, and this equation gives relationship between excess pressure as well as surface tension and the radius of the drop. This equation was developed by Laplace. Therefore it is called as the Laplace law of spherical membrane. Now we can also develop Laplace law for liquid bubble. Liquid bubble has two surfaces. One is the inside surface and second one is the outside surface. So when you are blowing it, then its surface area increasing. So inside surface is increasing as well as outside surface increasing. Both are increasing. This is the inside surface is increasing and here is the outside surface as well as increasing. So this is the thickness of it. So inside surface increasing as well as outside surface increasing. So increase in the area, we have to consider increase in the inside surface area as well as increase in the outside surface area. So total increase in the area dA equals to 8 pi r delta r plus 8 pi r delta r, that is equals to 16 pi r dr. This is nothing but increase in the surface area of the liquid bubble. Now again we have to calculate the stored energy. For that, the dE1 we have to calculate. That is the dE1, the energy stored in the surface of the bubble by using surface tension formula. That is T is the surface tension and dA nothing but 16 pi r delta r. So energy calculated, stored energy calculated by using surface tension formula. Now we can also calculate the stored energy by using force into displacement, force into distance, force into thickness of the film increased. So dE2 nothing but Pi minus P naught multiplied by 4 pi r square delta r. Both energies are calculated by using different formulae, but the results are equal. Therefore dE1 equals to dE2. So dE1 is nothing but T into 16 pi r delta r and dE2 nothing but Pi minus P naught multiplied by 4 pi square delta r. When you simplify this equation, you will get Pi minus P naught equals to 40 upon r. So Pi minus P naught equals to 40 upon r. This is a Laplace law for spherical bubble. It is a, and for the drop it was 2t upon r, and for bubble it is 4t upon r. So Pi minus P naught equal to 40 upon r. This is nothing but Laplace law for spherical bubble.